So today, just kind of a fill-in lecture that kind of connects a lot of the things we've been talking about to more fundamental concepts and tries to explain. Tries to explain where some of these requirements come from that we need in these statistical tests. So I can get my focus back to Zoom or to here. There we go. Basic announcements, the big thing now is this input modeling report. So I met with some teams in office hours asking about, different aspects of this, which systems to select, and I have all these sorts of things. And I guess the thing I want to emphasize is that you should select a system that is tractable. It's easy to get access to, easy to find data to, has a simple question that you can address in about a half semester. So don't try to be super ambitious, but you also want to make sure you select a system where the question you're asking, the operations question you're asking, is interesting enough to warrant using simulation. If it's something that you could say, well, how do we make service faster? Well, we add another cashier. Well, we know that adding another cashier is probably going to make service faster. And so that by itself isn't, that interesting. But if you get into these things like, how many cashiers will it take for a particular threshold to occur? Is there another technology we can introduce? Is there another way we could organize how things are made so that maybe we eliminate some bottleneck, and so on and so forth? It is okay if some of the variables that you need to put in your sim are really hard to get data on from the real system. You can make assumptions about them. You can Google for other examples, or you could just sort of use your background knowledge and say, well, we don't really know, but from personal experience, it seems like it should be no less than X and no greater than Y. So we're using a uniform distribution for this. And then you could do a sensitivity analysis and say, and let's say our assumptions were wrong about this particular input. Let's make it much longer or much shorter, and then see if it changes our recommendations. And if it doesn't, then that's great. Then you could say that our recommendations are insensitive to this parameter that we didn't have. If it does change things, then it's an awesome output to be able to say, a next step in this project that you wouldn't do, but you'd be suggesting that your stakeholders do, is to invest in gathering more data about this particularly sensitive spot. So that's kind of what you should be thinking about as you're choosing your systems. The other thing I want to emphasize is the input modeling report is not a contract on your choice. Choose something that you can write up this short input modeling report on that shows me that you have momentum. But if you find out later that really it was better for you to switch to a different system, I'm not going to check that your final project report matches your input modeling report. So it's totally okay to switch later on if you have a plan B. Otherwise, we've got these two labs, 9, where you're going to learn how to compare outputs quantitatively using some tools inside Arena. And then lab 10, where you're going to learn about things like batching and signaling, a little more advanced topics in Arena, but very useful topics in Arena. And then otherwise, we've got labs for final project modeling help. So yeah, this is just kind of summarizing what I've been saying here. This is just kind of in text what I was just talking about. Otherwise, we've got these ICAs. This homework is out and still posted. It's due in about a week. And after it's done, then homework J2 is the last homework, and it's an Arena-based assignment. So any questions about the project report or the input modeling report coming up, or selecting a project or anything along those lines, schedule otherwise? Questions online? Okay. All right, so this is my annual Halloween stats lecture. So I usually have a Halloween themed stats lecture every semester. And so one of the 475 students thought that I should have this in it as well. So this was contributed by a former student of 475, thought it fit in pretty well. I added the happy Halloween, that was all me. I'll find that there's, as I may have been hinting in some of my previous examples, I actually think that Halloween is a really nice context for thinking about hypothesis testing. And we'll see about what I mean by that here in a moment. So, this is all should, just keep reviewing the same stuff, type 1 error, alpha, significance level, type 1 error, false positive rate. If we calculate p-values, that's the modern way to do hypothesis testing. If your p-value is less than some threshold set by your context, it's usually 0.05, but in medical applications, it might be 0.01. In other applications, it might be higher. In engineering, we actually often set alpha. If we're doing research and development, our research and development budgets are usually high enough that we can do further investigations if we sniff out a particular thing that might save us money down the line. So in engineering, you actually sometimes might set alpha at a 0.1. So what that would basically mean is even if there isn't an effect of some new thing that you've introduced into a process, if there's a hint of that effect, you might want to detect it. Because then if you can, in a pilot study, detect that there might be an effect there, then that might warrant getting your boss, who has maybe deeper pockets, to invest in a more significant study. So alpha is really, it's how much, you're trying to detect differences due to some intervention that you've added. And the higher the alpha, the more likely you are to detect even smaller differences. That's one way to think of alpha. And then likewise, beta is the flip side of that. So that's type 2 error, false negative rate, FNR. And so, we think of this as there really was an effect there, but we didn't detect it because it was so small that it was buried in what we'd expect from a non-effect case. And so the flip side of beta is statistical power 1 minus beta, which we also call sensitivity, or TPR, true positive rate. And so this is relates to that idea that I was just saying, that if the effect is super small, in other words, if it's very similar to what you'd expect without the intervention, then it can be confused as to having no effect whatsoever. And so if you have a test with high statistical power, it allows you to detect really tiny effects. And so, so that's oftentimes, if we're looking for rejecting a hypothesis, just detecting something, then all we really care about is alpha. But if we really do think that our null hypothesis might be true, and we want evidence that our null hypothesis really is true, then we need a test with high statistical power, because that will say that the deviations we see are going to be small, because if they were slightly larger, then we would have gotten a rejection of the null. So high statistical power and low alpha are these things, but they trade off against each other, as we talked about last time. So a test power is modulated by, if the data you get are really variable, that's going to give a lower power result unless you increase the samples. So for a given test, if you sample more, you'll get more power. Or if you somehow can redesign your experiment to have less variability, and we'll see an example of how you kind of do that in just a little bit. So if you can manage to reduce the variability in your design or increase your samples, you will get more power out for the same test. Now, across tests, there's some tests that are naturally have higher power. So a Kolmogorov-Smirnov test has higher power than a chi-squared, just naturally. And so the downside of that is it can detect really small differences that might be insignificant practically, even though they're statistically significant. So as you'll see in part 2 of the homework, a power analysis helps you decide how many samples you need for a given power that you want, or to detect a specific difference. So if you want to detect differences that are so big, then this will say, well, then you need to make sure you sample at least 10 times. And so we'll see an example of that today. And that's what you're going to be doing in part 2 of your homework. So this is the common table that we'll sort of use to kind of cut these things up here. So if we kind of focus on the null hypothesis here, then we can say that there's these columns are like when the null hypothesis is true and the null hypothesis is false. And down here, I've flipped the interpretation to say not the null, but an alternative hypothesis. So when the null hypothesis is true, then an alternative hypothesis is false. When the null hypothesis is false, an alternative hypothesis is true. I don't like using focusing on an alternative hypothesis because there can be lots of alternative hypotheses, not just a null. And so the null is sort of, you're saying like, this is the one null. But if the null is false, it could be due to a lot of other things. And so that's why we usually don't talk about the alternative. We talk about many alternatives, which all might have a possibility of rejecting a single null. But sometimes it's easier to conceptualize thinking not about the null being true, but an alternative being false, and vice versa. So this is the same table up here and down here, but we just are using slightly different terminology. So up in this table, I'm saying the upper left-hand corner is our type 1 error rate. Down here, I call it a false positive rate. And so here, positive is meaning that we're detecting a difference from the null. So that's the good thing. It's like the null is what happens every day. The alternative is saying that this isn't what happens every day. We've actually made a difference. Turning up the temperature in the factory increased the speed of the process. We wanted to detect that turning up the temperature actually made a difference. That's a good thing. So that's a positive result. We have detected a difference from the norm. So that's why we use the term positive typically to mean rejecting a null. So rejecting the null is a positive. And if you falsely reject the null, that's a type 1 error, otherwise known as a false positive rate conventionally. Similarly, if you fail to reject a null when the null wasn't true, then we saw that a type 2 error, but we'll also typically call a false negative. So we're saying positives are rejections, negatives are non-rejections. And then the statistical power, it falls into this top right box where the null is false and we reject it. Then this is the box. By these boxes, I could basically say, if you consider a bunch of different tests, some when the hypothesis is true, some when the hypothesis is false, how do they break up among these 4 boxes? And so we're saying this green box are all of the tests that correctly reject a null when the null is false. And that fraction is what we refer to as the statistical power, or 1 minus beta. So the true positive rate is another name for statistical power. We don't really have another name for the true negative rate, but because we typically focus more on statistical power and false positive. So these 2 boxes that are next to each other, FPR and TPR, those are the 2 things that we typically talk about when we talk about hypothesis tests. Now, any questions about this interpretation, about positives being rejections? So it's like if you took a pregnancy test and the null would be that you're not pregnant. It would be just as normal everyday physiology. And so in that case, a positive result would be detecting a deviation from normal body physiology, i.e. deviation equals pregnant. So if you're not pregnant and it says you're pregnant, we call that a false positive. So, so positive has to do with, you really have to focus your mind on what the null is, and it should go down to what is the normal everyday thing, and I'm detecting a difference from that. All right, so, but that said, and let me see, are there any questions online too? I'm gonna make sure this terminology is clear. Sometimes when you talk to different stakeholders, they have a different idea in their head what positive and negative means. And this is a reason why I don't recommend using the terms false positive and false negative in front of general stakeholders. Only use those terms in front of a statistical audience where you're all going to agree on what a positive and negative is. Because a lot of times your stakeholders might have this in mind. Because if you say to them that my null hypothesis is what I'm testing for, then they're going to think that a positive result might occur in the column where the null is true. And if you fail to reject it, we're calling that a true positive. So it's like a lot of times stakeholders focus on the null, and in which case, because we talk about the null, then you would think a negative would be rejecting the null and a positive would be accepting the null. But that's not it. A positive result is detecting a deviation from the null. And so that's the conventional terminology. But a lot of people will end up taking on this terminology. So you have to be really, really careful if you use positive and negative in your speech, because a lot of times people don't agree on what positive and negative is. And that's a big reason why I really like, I'd prefer to use things like type 1 error, type 2 error, because it's very clear where the null is and how we're referring to it. So this is kind of a nice parlance we can all use. This you have to be careful about. That said, in this class, I will be using some of these, periodically, because in a statistical audience, it's very common to use these. And when I say positive, I mean a rejection. So false positive rate to me is type 1 error. Okay. All right, so kind of think about alpha and beta and kind of a Halloween sort of thing. Like if we think about, it's a movie from my childhood, Ghostbusters, then the idea here is that, there's a group of people who are ready to believe you. So most people would say there's no way there's a ghost in your house. It's just a cat that ran across the back or whatever. And that would be the null hypothesis. The null hypothesis is it's not a ghost. It's just everyday whatever. When they say we're ready to believe you, what they're saying is that their alpha is much higher than everyone else's alpha. It's much higher than 0.05. And so the idea there is that they're sort of like beta busters. And so their beta is much lower than everyone else's. In other words, they're okay with having a lot more false positives because they want to reduce the chance of false negatives. So a false negative would be like there actually is a ghost, but you just assume that there's not a ghost. And so in this application space, beta is much worse than alpha, in part because their business is built on finding ghosts, right? So if there are ghosts out there, they want to find every single ghost, and they're totally fine with coming out and not finding the ghost. It's similar to like, a plumbing company or whatever. They always want to come out and just do an inspection, even though they have no reason to believe there's anything wrong with your plumbing or your air conditioning or whatever. They always want to tune up. And usually a tune-up is they look at the thermostat and they maybe check for leaks or whatever, but there's really no reason to believe that they need to be there, but they want to come anyway. And they spend the time to send somebody out because every once in a while, somebody really will need service, and that is a big payoff for them. So a lot of businesses are built on a low beta, or in other words, a high alpha, because these things go along. And that's what I mean by engineering, research, and development too. If your job is to figure out how to improve a process, and there's a bunch of low-hanging fruit that are out there, it might be that without engineering, the effect of all those low-hanging fruit are small. But your job is to use a substantial budget to go out and just see what the small effects of each one of those are, because then it could become an engineering problem to expand those effects. So if you're in business or in engineering, you might want to set your alpha much higher in order to reduce your beta, because you want to catch everything, and you're okay with sometimes catching a wrong thing, because then you've got enough resources. Like the ROI on the whole venture is going to be so good that it's okay that every once in a while you go down a kind of a wild goose chase. So, so it's kind of the perspective I want you to kind of get here, is that when we talk about 0.05 in this class, but in reality, different applications are going to have higher alphas in order to get lower betas. And it's just that trade-off. All right, does that make sense? What I mean here, that alpha equal 0.05 is not a universal truth, that you have to be prepared that sometimes you actually are okay. You tolerate more false positives because it's good for business. Okay. All right, so this is hopefully a curve you've probably seen before here, which kind of captures all of these ideas in one. So this is sort of based on a t-test, and I can show you the same curve for a chi-squared test. And the idea here is that everything kind of under this left curve, or this left curve here that's mostly blue, those are the test statistics. So let's say a t statistic, or a chi-squared statistic, or a ks statistic under the null. So if you assume it's the everyday occurrence, then this is the distribution of, let's say we go back to the ghost example, then if there are no ghosts and it's just cats and dogs and wind, then this is the distribution of all the sounds that you would hear. So the test statistic in that case might be the amplitude of the sound that you hear as wind or cats or whatever are walking over your back patio. And so that's what's captured by this whole curve. Now, you might say that if a noise is loud enough, then we're going to say that that's abnormal. So what you define as loud enough is going to be different than what I define as loud enough. And that's what this threshold is up here. So anything to the right of this threshold is so loud that you're going to say that's not normal. And anything to the left of this is within the normal range. And so that corresponds to a critical value in a statistical test, like a critical t value or chi-squared value or ks value. And there really might be the case that there's something else going on, be it a ghost or be it a water leak or whatever. And these are the sounds that would be generated under that particular alternative hypothesis. Now, we don't know what all the alternatives are. So typically what we do is we try to consider an alternative hypothesis whose mean value is far enough away from the mean value of our null. And we sort of say, like, if it was that type of hypothesis or worse, then what would this kind of curve look like? And so what I'm trying to capture here is as you move this threshold over, then so like right now, it looks not so bad in that most of the outcomes that are to the right of this threshold are coming from the actual deviation from reality, which is this alternative hypothesis here. But if I move this threshold farther over to the right, then what I reduce some of the outcomes that come from the null, the everyday, which is good, but I also start reducing some of the outcomes from the true positive as well. So if my threshold's like way over here, so that then none of these outcomes, true or false, will actually be to the right of that threshold. And if my threshold's way over here, all of the outcomes, true or not, will be to the right of that. And so this is what I mean when I say what you set alpha equal to 0 or alpha equal to 1. When I set alpha equal to 0, we never reject. Well, what does it mean to never reject? Well, that means to have the threshold way over here so that every outcome is to the left of it. When I set alpha equal to 1, always reject, then that means I set my threshold way over here so that all of my outcomes, true or false, or true or alternative, or null or alternative, are to the right of it. And so what we can do is to capture this idea of what happens when you slide this threshold back and forth, then we put that in this receiver operating characteristic curve, or ROC curve. And in that, it plots the type 1 error and the true positive rate, statistical power. So it's got the type 1 error, which is our false positive rate, FP, and the true positive rate, statistical power here. And the points along this curve correspond to the areas that accumulate as you move the threshold around. So moving the threshold left and right corresponds to moving this dot right and left on this curve. And so over here, where alpha is equal to 1, that's when the dot is all the way over here. Then I get 100% statistical power, but also 100% type 1 error, because alpha is equal to 1. And that's the case where my threshold is way over here. So it might be that I get a ton of statistical power. I will find every ghost, but it will also be the case that I will send the Ghostbusters or the plumbers or the HVAC people out to a bunch of houses that don't need their service. So this is not ever sending anyone out. This is sending them out everywhere. And there is some balance in between that. And so per your application, you're going to choose an alpha. And by choosing an alpha, you're effectively also choosing a statistical power or a beta. And the whole thing is taking this threshold and moving it around. And so this is our everyday. These are things that we would like to detect that are different from every day. So this is a type of, I want you to get to the point where this looks completely natural. So if I were to show you a graph that looks like this, you'd be able to describe every area of that graph. Like this little FP here, these are outcomes that are from the null, from the everyday, but they happen to be to the right of this curve. So those are our little false positives. These are things that are outcomes that are from the alternative, and they're to the right of our threshold. So there are true positives. These are outcomes down here are false negatives that are to the left of our threshold, but they're from our alternative. So those are false negatives. And then these here are outcomes to the left of the threshold that are from our everyday null hypothesis. So there are the true negatives. So I want you to be able to sort of understand the 4 regions inside here and understand how they effectively generate that ROC curve. If you have that in your head, this whole alpha, beta, false positive, false negative, all that just naturally falls into place. It becomes really intuitive. All right, so any questions about this image? And hopefully you've seen things like this before. I think like when I asked you what is alpha, people a lot of times bring up like curves. And so I think a lot of times alpha is defined with these curves, but I want you to think of alpha more broadly. You know, it's not with respect to any sort of curve, but now that we have that broad definition of alpha, if I were to show you these curves, you could connect alpha to it. And then likewise connect this curve to this curve. Okay. All right, so I mentioned that this bell-shaped curve is kind of the example for a t-test. Well, let's remind ourselves what a t-test is, and because we'll have to use a t-test on that homework. And I'm going to hop back to some slides we missed at the last one. So a t-test, as you probably know, was developed Guinness Brewing. So it was in 1908. This guy, William Seeley Gossett, he was effectively an operations researcher, an industrial engineer at Guinness Brewery. And they were making batches of beer, and they wanted to be able to detect differences in their batches of beer without having to make huge numbers, huge batches, and then kind of compare them just based on averages. So in agriculture, if you had a difference in like agricultural, you know, in some sort of agricultural operation, you'd have a giant plot of corn on one side, another giant plot of corn on the other side. And you could just look at sort of what's the average yield from my 2 different plots. And just if you compare the averages, then there would always be a noticeable difference. But Guinness was saying, or what Gossett was saying at Guinness is like, it's a huge waste for us to make a whole bunch of extra beer and just to find out that this whole batch is bad. So wouldn't it be great if we could just make, you know, a small sample of beer and a small sample of beer with the other treatment, and then find out from the small sample that the differences aren't just due to random chance, that the differences are due to our treatment. And so Gossett actually went and met with biologists who worked in agriculture. Biometricians is what they call it. Biometry is what statistics is called in biology. And biometry at that time was all large sample, like agriculture type of stuff. But he worked with, I think, Pearson to come up with this t-test, came back to Guinness. It was a real success. And he said, hey, Guinness, this could really be useful to the broader community. It's not going to really hurt our competitive advantage, you know, by distributing the t-test. Is there a way that I can publish this? And Guinness said, you can publish it, but they sort of said behind, you know, under the table or something at the pub. Yes, you can publish it, but formally, you're not allowed to publish things under your name because everything that you develop here at Guinness is owned by us, and we don't want to publish this, but we get your point. So if you can publish it under a pen name, and so Gossett decided to publish it under the name Student, and that's where we got Student's t-test. So a lot of times people hear about the Student's t-test and they think it's like if you're taking AP programming or something like that, it's like it was just developed for classrooms or something. But no, it's just a pen name that Gossett used to deal with the intellectual property laws at Guinness. And so it is a very real thing that is used in industry, and it's not just for students, but Gossett is the student. So, so it was later generalized into things like ANOVA by Fisher for a larger number of treatments, not just 2. It was then generalized for non-parametrics, which we'll talk about later in the semester, like the Mann-Whitney U test, and so on and so forth. And it's a pretty simple idea. So as you've seen before, I'm sure, this is the t-statistic. You got a bunch of data, and you go out and you take the mean, the sample mean of those data, and you also have a hypothetical mean that you're trying to see do these data, are they likely to have come from a distribution with this mean? And then you take the sample standard deviation from those data, divide it by the square root of n, and we're going to see why the square root of n here in a second. And that generates a statistic, a t statistic. And we compare that t statistic to a table. And if it's large enough, then that means that it's unlikely that these data came from that mean. And if it is small enough, then it is likely they did. So we refer to this as, so our hypothetical value here, that's the mu, that's the hypothetical, what we, hypothetically speaking, the random variable y has the mean mu. That's where that comes from. And we refer to this as a one sample t-test. When I was in your seats, this was confusing to me because I took more than one sample, right? I took 100 samples. Why am I using a one sample t-test when I have 100 data points? But the one sample they're referring to is the sample mean. So it's the idea there that you take your 100 data points and you compress them into a single number that is that one, and that is the one sample. So it's technically you're sampling from a distribution of empirical means. And this is the one sample from that distribution. So that's the reason why it's called a one sample t-test, because in the t statistic, you don't put all your data, you put a single approximation of your data, that one y hat or y bar. So in order for this to work, we need the data that generated that y bar to have been drawn independently, and we need the data to come from a normal distribution. And under the null hypothesis, that normal distribution will have this hypothetical mean mu. And so under those assumptions, if we are under our null hypothesis of this mean, if everything's normal, and if all the samples are independent, then this expression will have what's referred to as the student's t distribution, which is the thing that Gossett came up with. And that will end up being the tool that gives us a measuring stick to say, does the t statistic that we found, is it as likely to have come from this null or not? Because if the null was true, then this statistic, if it's way on the tail of that distribution, then it is unlikely to have come from the null. Because if the null was true, the only way you'd get that value is if it was really, really rare. So that's what allows us to set this threshold up. So where does this come from? So, this is, we're going to take these assumptions of the t-test. Each point is independent. Each point is normally distributed with the same mean and the same variance. We're assuming the null is true. If we take this y bar calculation, just the sample mean, this is our expression for sample mean. We can break it up, just arithmetic there. And then under the null hypothesis, each one of these samples should have the mean mu. So the expected value of this sum, considering they're all divided by n, is going to be n times mu divided by n. Because there's n of these, and they're each divided by n, which so the expected value of this sum divided by n is just mu. And then if we take this y bar and subtract off the null, the expected value of this sample mean is 0, or the sample mean minus mu is 0. So if you take a bunch of data and you calculate y bar minus mu over and over and over again for different samples of data, then it's going to be clustered around 0. Its mean will be 0. So then we can also calculate the variance of this thing. And you do a little bit of probability, and you can find that the variance of y bar is actually equal to sigma divided by square root of n. And where does the square root of n come from? Well, it turns out that the variance of this thing is just the variance, is the sum of all these individual variances. So you get n times these variances, which are each the variance of the null hypothesis. So you end up getting the variance is sigma squared divided by n. And so then you take the standard deviation, and that's where the square root of n comes out here. So this so-called standard error of the mean, the square root of n looks a little funny. Like, where does that come from? It comes from dividing the variance by the number of samples here. So it's sort of less important that it's standard deviation divided by square root of n. It's more that it's variance divided by n. And we just happen to take the square root of that to get standard deviation. So that's where this SEM formula that we should be familiar with here. So now we've got a mean of this quantity, y hat minus mu, it's equal to 0. And we've got a standard error of this mean, which is sigma divided by square root of n. So this is just describing the distribution of values that we get by doing this y bar calculation for different data sets. And so we can take those things here, and we know that under the null hypothesis, if I take the number of samples to infinity, then this y bar minus mu is going to be equal to a normal distribution with mean 0 and standard deviation this. So just by the central limit theorem, because this is a sum, if I take the number of terms in the sum to infinity, then this quantity y hat, which is just this average minus the mean, is just going to be a normal distribution centered around 0 with this standard deviation. So if I further take that and just create effectively a z-score, a standardized score, this is just a mean value divided by the standard deviation, then this new value I get, which I'm just going to call t, that new value is going to have a mean of 0, but its variance is going to be equal to 1. In other words, as if I have a large number of samples, this t statistic under the null will be normally distributed as a standard normal. So that's the motivation behind the t-test, was that we know that this average is going to be normally distributed under the null if we take a lot of data. And so large sample statistics all just use normal distributions, because everything was normal, because in large sample statistics, you're taking averages. Averages are sums of large number of terms, central limit theorem, all go to the normal. So what Gossett added to this was he said, well, what happens with small n? And he figured out, he solved for the expression for this distribution for small n. And so he was able to, so I've got in blue the standard normal. And if I have 1 degree of freedom, which is 2 sample points, and I calculate this t statistic under the null, then I get this thing, which is shorter than the normal and has much fatter tails. So it's a symmetric distribution, normal-like, but it is not quite normal. And so it's got more values that are out here in the extremes. If I add another point to it, so now the red curve is with 2 degrees of freedom, so that's 3 sample points, because I subtract 1 due to estimating the mean, then it gets a little closer to the normal. If I go further up, 3 degrees of freedom, closer and closer to the normal, 5, 10, and so on. So the t distribution becomes the standard normal with large data set, or large amounts of data. So if you have a large amount of data, you can just use a z-test. It doesn't have to be a t-test. A z-test is perfectly fine, because a t-test approximates a z-test. But a t-test, like really strong point, is when you have a small amount of data, then it describes the null much better than a standard normal. And that's where we get the t-test. So a t-score turns into a z-score at high n. At low n, it's its own thing. But conceptually, you can think of it as like a type of z-score. So that's where the t-test comes from. So we call t a pivotal quantity. Its shape only depends on the number of samples, the degrees of freedom. And so for any normally distributed hypothesis, t has the same distribution. And so that's what allows us to use to calculate a t statistic and set a threshold, regardless of what our hypothesis is. Our hypothesis might be that under normal situations, we get this acoustic level. Under other situations, we get this acoustic level. It doesn't matter. As long as it's normally distributed, we can plug in the values and, and we'll be able to evaluate our deviation from the null using this t distribution. So that's the magic of the t-test. And so a very rare t is evidence of an unlikely H0. Now, that I was describing was for a 1 sample t-test. We can also do this for a 2 sample t-test, where instead of using a null that you assume like 5, you could just say I've got 1 data set and another data set, do they come from the same distribution? And that's the so-called two-sample t-test. So, that's kind of where this curve comes from here. This here is kind of viewed as a t-distribution. It sort of looks like a null distribution, but you can kind of view this as like, well, a t-distribution, I'm sorry, it looks like a normal distribution, but a t-distribution is also symmetric. It just happens to have fatter tails and it's shorter. And that's kind of where this, this kind of joke comes from here. So this is a grad student in statistics, and he has this t-shirt that he's made. I've already kind of given away part of it. And notice the t-shirt says student down here, and it shows a symmetric bell curve with really fat tails on both sides here. And so hopefully if you stare at this for a little bit, you can see that the joke here is this is student's t-shirt, because it's a t-shirt with the student's t distribution on it. And on top of that, you can make further jokes like, this isn't a normal student, right? So it's a little bit weird. It's a t distribution, you know, so it's not normal. And likewise, in this particular picture, this stat student carried around a box of tea all night and had a bottle of Guinness as, again, an homage to the test and to the company that gave us the test. So hopefully that makes sense. So now when you see things that are bell-shaped, that have fat tails, your head should go to t distribution, not normal distribution. All right, so yeah, students' t-shirts, not a normal student. Okay, so any questions about that, where we get the normal distribution? And I hope it, some of the things I tried to make clear there, went maybe by a little fast, is that a lot of the variance calculations that we got there required independence. And there were a couple of other things there that in order to do that derivation, we really needed to assume that the null hypothesis comes from a normal distribution. So this is a big reason why before you do a t-test, you have to do something like a Shapiro-Wilk to guarantee that your data is from a normal distribution. Otherwise, you have to use a test that doesn't depend on normality, and we'll talk about those later. All right, so, and that's kind of, I think, what I'm sort of saying here, is that if normality does not hold in your data, then you can't use a t-test, because a t-test depends on normality to give you that nice curve. And so later on in history, then others started to make tests that work like the t-test, but don't require normality. And the one that we talk about the most here is the so-called U-test. Well, you just remember, it's the one that comes after t. So a t-test and a U-test. A U-test is a t-test which doesn't require normality. The downside is it has less statistical power. So the more you can assume about your data, the more statistical power you get. That's why we prefer to use a t-test, but if we can't, there are alternatives that are out there. So as you'll learn, you'll come out of undergrad and you'll have learned all these parametric tests, t-test, chi-squared test, etc. Well, chi-squared is a little different, but t-test, ANOVA, or whatever. And then you're going to hit the real world and you're going to find out that not everything's normal. So if you just Google for what's a non-parametric t-test, it'll pop up. Oh, that's a Mann-Whitney U-test. And then you already know how to use a t-test, and your stats program is already going to have a U-test loaded into it. You're not going to have to hand do it. And then you can use the exact same reasoning. The only downside is the U-test is going to be far less sensitive than the t-test. So you lose power if you can't assume normality. All right, so any questions on that? Okay. All right, so there was an example that I want to tab back, and this is the tail end of this example from last time. And I just want to bring up, because it relates to the homework. Oh, I had it a second ago, there it is. It's just in. All right, so we talked about this last time, this bank example, where we're trying to model a bank. And we talked about how there's different variables in the bank. There's the inputs, the decision variables, the outputs. We use input modeling for the inputs. We simulate, we get to a bunch of output variables, and we want to compare how the real system's outputs look like the simulated's outputs, and that gives us confidence that our model is valid. And so in this particular case here, I am going to collect system response data from the simulation. So the simulation, I'm going to call them Y as the output, and the real system. So the simulation data I'm going to call Y, the real system I'm going to call Z, and I'm going to collect them during the same time period of the day. So if I simulate, I always collect from the real system from like 2 o'clock to 3 o'clock. And that way my simulation is going to match 2 o'clock to 3 o'clock. Now, following on what we just talked about with the t-test, then the idea here is if I take my real data and I see that it has a mean of 4.3 minutes, then if I built my sim correctly, then my sim's mean should be 4.3 minutes. Now, because the sim has got random outputs, it's not going to be exactly 4.3. So we need to say, what's the likelihood that the data that I got out of the sim came from a distribution that had a 4.3 mean, which matches my reality. And so my null is that my mean of my sim matches the mean of the real. And I need to choose a number of replications to run of my sim to estimate this. And so that's something that involves the statistical power that we're getting into try to calculate here. So for each replication, I'm going to calculate for verification to make sure I implemented my sim correctly, the average number of arrivals per hour and average service time, because I know what those should be, because I model them as my input model. And then for validation, I'm going to measure the average delay. And I get a data table that looks like this. So I ran 6 replications here in my simulation. These were my arrivals per hour from the first day I simulated, the second day all the way up to the 6th day. Here are, I think that Y2 was the average service time from that day and so on. I can confirm that these, I expected these to have an average of 1 or something. I expected these to have an average of, 50, and I can confirm that. And that tells me, okay, good. So I put the right parameters into Arena. I didn't screw up. So that's my debugging. Like that's the reason why I might output those, even though I technically forced them. So that's just a sanity check. The validation step is to look at the outputs here, and I get a bunch of data here. So of these 6 samples, these are each one of the average delays across customers across day 1, day 2, all the way up to day 6. I can take an average of those, 2.51, and its standard deviation, 0.82, and I want to know, is it likely that this average, 2.51, with this standard deviation, 0.82, would be described by a distribution whose mean matches the mean I got in the real system? So that's where I go to my my student's t-test. And so we did already talk about all this a second ago. So now I get to calculate that t-value. So I've got my average from my sim is 2.51. My standard deviation from my sim is 0.82. So I calculate this t-statistic, and it's minus 5.34. Now, this was testing against a hypothetical null of 4.3. So what we're saying is that for this standard deviation, assuming that the standard deviation matches from my real system and my sim system, we take that as an assumption. Is it possible that the data that I got here, this mean that I got from 6 replications, could have possibly been from a distribution whose real mean was 4.3? And what this tells me is that if I look up for an alpha of 0.05 and an n of 6 in the back of the book, the critical value is 2.571 for the absolute value of that. Well, the absolute value of this is way bigger than 2.571. So that tells me that the deviation that I'm seeing in my sim is way too big. And so most likely my sim doesn't match reality. So that means I need to go back to my sim and see what I left out. So I take corrective action and I say, well, what didn't I model in the sim, or what did I model? What assumptions did I make? I said, well, one of the things is I assume there's no delay between one service ending and the next beginning. Maybe that's a bad assumption, but then it turns out it looks like that's pretty right. But it turns out here that The big thing is I assume that when a car arrives to the window, the teller is immediately available. But when I actually go and look at the system, a bunch of times the cars pull up to the window and the teller is nowhere to be found. They have to wait for the teller. And that it then occurs to me that the teller is also servicing walk-in customers, and I didn't model walk-in customers. So even though I want to model just the drive-through, it's impossible for me to model just the drive-through without also modeling the walk-in customers, because they're putting a load on my central resource, the tellers. So that tells me that I'm going to go and rebuild my sim, including walk-in customer inputs as well. And after I do that, I redo this whole experiment. I get my sim table. I calculate a t-statistic out, and I end up finding that the value of my t-statistic out now is well below that threshold. So that tells me that I at least have some confidence in that maybe this simulation actually matches what's going on in reality. But I don't know for sure that I can actually say that my sim is reality. It really could just be that I only took 6 replications, and that's such a low value that my test wasn't sensitive to detect the difference there. So I have to confirm that my test has sufficiently high statistical power. I need to actually say, what is the statistical power for this test? And so that's where we do a power analysis. And so, as we talked about at the beginning of class, beta and 1 minus beta. So we can do a power analysis for a 1 sample 2-sided t-test. And what we do is we calculate an effect size, and that effect size is going to be this is going to relate to how big, what's the minimum detectable difference in our means for us to consider them to be a different hypothesis, or for them to be considered to be not from the null. So if I tell you ahead of time that your sim needs to match the waiting time for real customers by a minute, then the numerator here will be a minute. I might say, actually, I'm okay with it matching within 10 minutes. The numerator here will be 10 minutes. So you have to decide at what point do things go from being close enough to the null to being may as well be the null to being definitely different from the null. And that threshold for what you consider to be null enough is what you put in the numerator here of this thing called effect size. You then divide that, you standardize it. So you divide it by the standard deviation of the system. And that's how you get this normalized or standardized effect size. Now, what do we do with that? Well, in the back of the book, there are these operating characteristic curves, not receiver operating characteristic curves. Unfortunately, there's a bunch of different types of OC curves, and these are just called operating characteristic curves. And they plot the false negative rate, beta, against the effect size for different values of alpha for a specific test, like a t-test. So in the back of the book, there is a table which gives us this curve for a t-test for alpha equal 0.05, and it's got beta on this axis, and it's got our alpha on this axis. So we calculate the alpha that we need for our desired detectable size, and then we ask, what is our acceptable beta? Well, if we want a statistical power of 80% or higher, then we want a beta of 20% or higher. And so I will, so usually 80% is a common one there. So I will tell you, I need a statistical power of 80% or higher before I let you accept the null hypothesis when it fails to reject. So you look at this curve and I say, well, an 80% power corresponds to a 20% false negative rate. I go across here until I hit whatever my effect size was. So let's say my effect size, my standardized effect size was 1. Well, if I go along this line, then that's going to tell me that I need at least 10 samples or more for my beta to be 20% or less. So that's what these curves are telling you. So if I allow for a 40%, for example, a 40% beta, then that means I need 7 samples or more. If I need a 10%, then I need to go over here and it's wherever, so it's somewhere at least 15 samples. So this curve allows me to see, did I have enough samples? And so if I were to calculate, if I were to tell you it's 1 minute and you divide it by a standard deviation of 2, then my effect size would be 0.5. I go here to 0.5, I'd go up, I'd see what hits 20%. Then I need 30 samples to be able to detect that, that effect size. And since I only had 6 samples, that's not enough. And I need to go back and collect more samples. If on the other hand, the standard deviation was maybe much smaller than that, and so I need to detect 1 minute, but the standard deviation is 0.5, then my effect size is out here at 2. And so now it looks like I need at least 5 samples to get that power. And I had 6 samples, so that's good enough. So then I can say, given that you were looking for an effect size of 2, I had enough samples for a failure to reject to be equivalent to an acceptance of the null, and the null being that our sim matches reality. And that's how we do a power analysis. So you're going to do that manually in your homework for the 2 sample case, which I'll revisit, which I've actually got an example of online. In moving forward in your career, you just let a computer do it for you. So in MATLAB, there's a program, a command called sample size power, and R called power, and it'll do all these calculations for you. All right, I'm happy to take questions after. Since I was late today, no worry about attendance, but I hope you have a good Halloween weekend. Again, feel free to come up if you've got any questions. Otherwise, we'll see you next week. Well, let me just close the mic here, and if there's nobody else. So any questions online? If not, I'll probably go ahead and end the call. All right. Have a good weekend.